Gnanam paramam dheyam. Knowledge is supreme.
So, let us say that we are going to do on induction number of rows 1 cross m, there is only one row in the matrix. Can you say it is in the row equivalent form? Obviously, because if it is non-zero, right, some zeros may be coming, first time there will be some non-zero if it is a non-zero matrix, that is fine, there is only one row, so nothing to worry, right. R1 is, R is 1 cross n, R has to be between 1 and n, so it is equal to 1. So, the proof that a row matrix, a row vector is in row equivalent form if it is non-zero, is it okay? By default it is non-zero, so it has to be in row equivalent form. So, induction starts, m equal to 1, the proof is, let us assume when the number of rows is something, it is okay. When number of rows becomes one more, how to do it, right. So, that is the question. So, let us look at that. So, let us say these are the rows of R1, R2, Rm. M is a non-zero matrix. So, it will have rows R1, R2, Rm. So, what one does is look at the columns of M. You are given a matrix, right. Look at the first column, possibly everything is 0 in that column, fine. So, what will the machine do? It will scan the first column, no non-zero entry, go to the second column, non-zero entry. So, look at a column where the first time it spots a non-zero entry in some place, we do not know where. So, let P1 be the first column that has a non-zero entry, first column 0, second column 0, the first column where non-zero entry somewhere comes is the column number P1. So, non-zero entry has come at some place, that we should make it as the first one, that should make as the row. So, that row should be made as the first row, because everything else was 0 on the left side of it. Is it clear to what we are doing? Look at the column 1, column 1 is all 0, scan column 2 all 0. At the P1 column, the first time a column has a non-zero entry is P1. Now, it will come at some place, say it is at the ith place. So, Pi P1 is non-zero, everything else on the left side is 0, right, everything at the top is also 0. So, what we do is we take this row and make it as the first row. So, what will happen? Everything else is 0, the first non-zero entry is coming at the place P1, right. So, first stage is achieved, the first non-zero row has a non-zero entry at a place P1. Everything on the left is 0, at the bottom we do not know what it is, right. But if there is a non-zero entry coming somewhere at the bottom, we can make that also 0 by row operations. So, everything below that can be made as 0, right. So, what we have gotten? P1 non-zero, everything below that is 0, everything on the left is 0. Now, again now start scanning the remaining part of the matrix. The remaining part of the matrix, what is the order of the remaining part? Already one row is gone, so one row less. So, by induction I should have row equivalent form for that. So, proof is over, right. So, it is done by scanning the columns, scan a column, non-zero entry, make it as the first row, right. Now, go to the next columns, spot the non-zero entry, make that as the second row, and everything below that keep on making it 0. So, that will make, right, that is a definite way of telling a machine that proceed this way, right, systematically, and in the end everything is over, everything is scanned, all the columns are scanned, your matrix will be in row equivalent form. So, that is what is written here. So, it says look at the columns of M, let P1 be the first column that has a non-zero entry, say ith place, first column non-zero entry. So, this is what the ith row will look like, 0 0 0, first non-zero entry coming here. Now that should be made as the first one, right. So change it. So change it to the first one. Something is there at the bottom, we do not know, but on the left everything is 0. These may be non-zero entries here at the bottom, but what we can do is by row operations I can make these entries as 0, right, by suitable multiplications. This is non-zero, divide by, right, multiply by the 1 over of that number, that will become 1, the negative of that, add it here, I can make this as 0, make this as 0, this as 0, right. So once a non-zero entry has come at a place, everything at the bottom can be made as, in that column can be made as 0 by elementary row operations. So I will have zeros here, I will have a non-zero entry here, and this will be all zeros. So what is left? Left is this part of my matrix, and that has order less than m, right, number of rows has reduced. Okay. So that will mean what? The number of these has reduced, that means by induction I can have that as in the row echelon form. I can go on applying this. I look at this column now and say a non-zero entry will possibly come here and change it in this part, in this part. So I will be looking only this matrix now. So look at this column here, non-zero entry coming here, I will shift it up and so on. Okay. That is the induction part. Okay. So that is how, so the second step was this is non-zero, everything else is made 0, right, which I said. Now look at this part and do the same thing, and now repeat the process on this part. So in your computer language, what you will say, do loop, right, it is a loop thing, on this matrix do the thing, everything will reduce, then do the remaining part and so on. So eventually apply this 1 and 4 in M1 and everything by induction you should have. So this is a definite way of doing things which can be fed to a machine also, right. Okay. So how do we use this row echelon form to solve system of linear equations? So we have a given system of linear equations, Ax is equal to b, right. Then we will make the augmented matrix, because b is going to be important. So this is a new matrix which has got one more column added to it, and we will reduce it to row echelon form, right. So I think let us give the video break and try to solve this problem now, then we will see the solution. So look at the system where the augmented matrix is given. Oh sorry, not actually it is in the row echelon form. So the example is already in that form, right. Is that okay? You are doing so that this matrix comes in the, A is the matrix. So let us discuss this example now. So this matrix A B, or A is already in the echelon form. Why? There is no non-zero row. Okay. First non-zero row, non-zero entry coming at 3, first column, second at second column, last as column 1, right. So how do you read this system now? This guy has come from a system of linear equations, right. So what is the new system now? This was variable x1, this was variable x2, this is variable x3, x4 and x5. So what does the last, when I multiply this with this, what do I get? Ax is equal to b. So it will give you x5 is equal to 4. Is it okay, the matrix multiplication? So reading is x5 is equal to, keep in mind x1, x2, x3, x4, x5, the columns are coming from the variables, right. So what is this equation? This is x5 equal to 4. What is this equation? 2x2, this is coming from x2, 2x2 minus 4x3 plus 4x4 plus 2x5 is equal to minus 6, and this gives you 3x1 minus 9x2 plus 12x3 minus 9x4 plus 6x5 is equal to 15. So your new system is that one, right. x4, x5 is equal to 4, so already value is known now. So, that value I can put in this equation, right. So, what I will get, I will put this value 2 times x 5, this will be a number now in the new equation. So, I will have 2 times x 2 minus 4 times x 3 plus 4 times x 4 plus 8 equal to minus 6. So, it has got only 3 variables, is the equation in 3 variables, right, as a relation between 3 variables equal to something constant, right. So, if I put values for 2 of them, I will get the third one, right. So, normally what one does is, one keeps the value where pivot is coming, you determine x 2 in terms of x 3 and x 4. So, that is backward substitution and giving arbitrary values. X 5 is already determined, you give arbitrary values to this variable and this variable, that is x 3 and x 4. So, for each value of x 3 and x 4, you will get a value of x 2. So, x 2 is known, x 3 is known, x 4 is known, x 5 is known, put that value back in the above equation, get x 1 in terms of those values, right. So, how many variables are getting arbitrary values? We gave arbitrary value to x 3, we gave arbitrary values to x 3 and we gave arbitrary value to x 4, x 5 was already determined. So, your general solution, right, will be determined by giving arbitrary values to x 2 and x 4, and these two variables can get infinite number of values, right. Each value will give you a value for x 1, x 2, x 3, x 4 and x 5. So, you will have infinite number of solutions where there are 2 variables getting arbitrary values, right. You can think of, there is a degree of independence kind of thing is 2, which are getting arbitrary. His question is, in this equation is 2 x 2 minus 4 x 3 plus 4 x 4 plus 2 x 5 equal to minus 6. In that equation x 5 equal to 4 we can put. So, I get a relation as 2 x 2 minus 4 x 3 plus 4 x 4 plus 8 equal to minus 6. So, 8 I can shift on the other side, I will get a relation between x 2, x 3 and x 4. X 3 and x 4 are now given arbitrary values. So, x 2 is determined in terms of those arbitrary values, or you can say x 2 can be determined in terms of x 2 and x 4 by shifting on the right hand side, right. So, for each value of x 2 and x 4, you will get a value of x 2, x 5 is already fixed. Now, for these values you can put back in this equation, the top one, right. You will get a value of x 1, which will be in terms of x 4 and x 3 and x 4, it will involve those values of x 3 and x 4, right. Yeah, but x 1 can be x 1 equal to in terms of x 2 and x 4. So, x 1 can also be determined in terms of x 2, x 3 and x 4. X 2 is determined in terms of x 3 and x 4. So, this is what is called backward substitution, go from the bottom to the up, substituting backward, whatever is arbitrary, put that arbitrary value, determine the next one from the upper equation and from the upper equation, right. So, let us, so x 4 is 5, I am just repeating that solution again, right, last equation. So, now second equation 2 x 2, shifting everything on the other side. So, that gives you a relation between x 3 and x 4, right. So, from this if I put x 3 and x 4 arbitrary values, I will get x 2, right. But I can keep this in terms of x 3, x 4 and put it in the first equation backward, that will give me 3 x 1 in terms of this, where x 5 is already known, right, x 3, x 4 in terms of 2, x 2 in terms of these two. So, if I put this value of x 2 here, I will get x 1 in terms of x 3 and x 4, right. So, x 1 in terms of x 2, x 3, x 4, x 2 in terms of x 3, x 4, x 5 is already known. So, your solution will involve only two variable quantities x 2 and x 4, which get arbitrary values, right. So, that is out the solution. So, let us do one more illustration, so that you understand. So, this is a system given. Okay. Once again, I already purposefully put in the row echelon form, so that we can analyze what is the backward substitution. Otherwise, you write A and B and reduce it to row echelon form, you will get something like this, right. Here it is already done, that A tilde B tilde. So, last row does not give you anything, is 0, forget about it, no information. What does this equation give you? This variable is, which is of this variable, x 1, x 2, x 3. So, it gives you minus x 3 is equal to 1, right. Minus 1 times x 3 is equal to 1. So, x 3 equal to minus 1. Okay. Look at this equation, it says 0 times x 1, so gone, 2 x 2, this is gone, 2 x 2 is equal to 1. So, x 2 is known. So, x 1 is known, x 2 is known. From this equation, what is the first equation now? X 1 plus 2 x 2 minus x 3 equal to 3, but all those two are already known. Put those values here backwards, you get x 1, right. So, in this system, there is only one solution possible, right. In this system, there is only one solution possible, and keep in mind what is R here. R is 3, which is equal to n, right. It is a minimum of, it is equal to n, the number of variable. See, if R is equal to n, that means pivots are going to, each pivot is going to come in each column. If R is equal to number of columns, then where are going to be the pivots? First pivot is in column 1, right. 1 has P 1, 2 has P 2. If the P 1, P 2, P R are equal to n columns, each column has to get a pivot, and that means there will be a unique solution. If each column has a pivot, it is going to be a unique solution, right. That is what is happening in this. So, these are observations we are putting, we will put them together. So, R is equal to n, the number of variables, right. Here P 2 is equal to 3, P 3 and n is equal to 3 actually. The system has a unique solution, right. That is what I was saying. So, P 1 is 1, P 2 is 2, P 3 is 3, there are only 3 columns, each one is having a pivot, right. That means everything will be determined uniquely, clear. So, R equal to n means unique solution. If R is less than n, then n minus R variables get independent values, arbitrary values, then infinite solutions come, right. If R is less than, then some columns will not have pivots, that means those variables will be determined in terms of the other one. Okay. Now, let us look at this another one, that means when I reduce the matrix A, aim is keep A and B side by side, aim is to make A in the row echelon form, go on changing B accordingly, do not bother about it. So, it gives you last row is 0, but here comes a row in A which is 0, but on the right hand side is come 3. So, what will this equation look like? 0 equal to 3, that means there is an absurd equation, there is one of the equations is never going to have a solution, that means the system cannot have a solution. So, if A P augmented matrix, when A is reduced to row echelon form, you find there is a row, right, where A, all the elements in that row are 0 in A, but the corresponding B is not 0, right, then the system cannot have a, that was the inconsistent I wrote in the beginning itself, allCij's are 0, but right Br is not equal to 0, right. So, that gives you a inconsistency. So, this is the way you will spot a inconsistency. So, 3 possibilities arise. One, the number of pivots, right, R is strictly less than n, the number of variables, then n minus R variables will get arbitrary values and remaining R will be determined in terms of this n minus r. Second, each column gets a pivot, n is equal to r, then unique solution, right. And third, there is a row 0 equal to non-zero, right. So, in that case no solution, inconsistent. So, three possibilities. Again look at 2 variables and 3 variables, 2 lines, either they are parallel, so no solution, they do not meet, right. Then 2 lines intersect, they will intersect only at a unique point, and then they are coincidental. So, when 2 lines are coincidental, then in the row echelon form one row will be 0, other will be relation between 2 variables. So, one variable will give the other value. So, infinite solutions, right. So, perfect similarity comes. Okay. So, this says R 3 is 3, P 1 is, so let us look back, P 1 is, this is P 1, first pivot 2, second pivot coming at the column 3, right. So, P 2 is coming at 3, right, last one is 5. So, 0 equal to 3 inconsistent. Okay. So, once again let us this row echelon form for solving a system of linear equations, summarize what we have done. So, he says look at the system A x is equal to b, a m cross n system with augmented matrix as A along with B, call it as M, augmented matrix we are calling it as M. So, reduce the matrix to the row echelon form and look at the non-zero rows. R is the number of non-zero rows for this, and pivots are coming at pith place, right. Then what? The system is inconsistent if there is a pivot in that column, right, the B column there is a non-zero pivot. If pivot comes there, that means all the previous must be 0, right. If in the augmented matrix there is a pivot lying in the column where B is coming, that means there is a non-zero entry in that, right. Everything else on the left side must be, what is the definition of a pivot? Everything on the left is 0. So, 0 equal to non-zero, that is inconsistent, system is inconsistent, that is what we saw, right. And if R is less than n, then there are n minus r parameters or variables, whatever you want to call them, which will determine a general solution, right. So, what we have done is for a system A x is equal to b, right, we take A and B, and reduce to row echelon form, right. Now, reducing a matrix to row echelon form is by scanning and interchanging or multiplying, right. Now, how does a computer know? I can't give a verbal command interchange, I have to give it in the form of something computational to the, you understand what I am saying? If you want to implement this command that interchange 2 rows, how does the computer understand that command? It can understand only multiplication, division, addition, arithmetic, right. So, what we are going to do is interchanging of 2 rows, that is one command, other is multiplying a matrix by a row by a non-zero scalar, second, and third is adding, right, adding one row to another. These ones we want to make it executable commands, so that a computer can understand, right. So, let us see how do we do it. So, let us how to execute row operations. So, that is what we want to understand. So, let us do some simple thing. So, let us take m equal to n equal to 3. Just for a square matrix we will take example for a 3 by 3. There is something called identity matrix. What is that? It is a 3 by 3 matrix. What does the entries look like? Along diagonal it is 1, everything else is 0. So, 1 0 0 0 1 0 0 0 1, right. Now, let us do those operations on this matrix and see what happens, right. So, interchange. So, this is R 1 and R 2. Let us look at that. Let us interchange R 1 with R 2 in this in identity matrix to get. So, what we will get? Let us see what do we get. So, we will get the matrix 0 1 0, R 2 has become R 1, 1 0 0 and 0 0 1, right. That is on identity matrix I have interchanged that done that operation. Now, let us take some other matrix A, whatever you like. Let us let us take 1 2 3 3 1 minus 1 4 0 5, some arbitrary matrix, right, and let us call this matrix as E 1 2, which we got after interchanging, right. I want to compute E 1 2 multiplied with A. I want to compute this. So, let us write 0 1 0 1 0 0 0 0 1 1 2 3 3 1 minus 1 4 0 5, right. Let us multiply them. What do we get? So, equal to, what will be the first entry? This row multiplied by this column added up. So, what I will get? 0 into 1 is 0, plus 1 into 3 is 3, plus 0 into 4. So, what is it? 3. Is it okay? What is the next one? This multiplied by the next one. 0 multiplied by 2 is 0, 1 multiplied by 1 is 1. So, plus 1, 0 multiplied by 0. So, that is 1. What is the next one? 0 1 0 multiplied by, so 0 multiplied by 3 is 0, 1 multiplied by minus 1, that is minus 1, and 0 multiplied by 5 is 0. So, that is minus 1. Is it okay? Let us do the next one. 1 0 0 multiplied by the first one. So, 1 goes to 1, 0 3 0 0 4 0. So, that gives me 1. Next one multiplied by the second one, 1 multiplied by 2 is 2, 0 multiplied by 1 is 0, 0 multiplied, so that is 2. And the next one, 1 multiplied by 3, both others are 0, so that is equal to 3. The last row, 0 0 1, 1 3 4, 0 0, and that is, so what does it give me? That gives me 4. 0 0 1 with the second one, 0 2 0, 0 1 0, and this gives you 0, that is 0. And the last one, 0 with 3 is 0, 0 with minus 1 is 0, 1 with 5 is 5, right. What is this matrix? This is precisely the matrix A with, this is precisely the matrix A with R 1 interchange with R 2, right. So, what we are saying is the following. Then if you want to make some operation on a matrix, so for an elementary row operation to be done on A, pre-multiply it with the matrix obtained from identity matrix by multiply obtained from by that operation. So, what we are saying is to give a command to a computer, how do I do that operation is take identity matrix, okay. Whatever operation you want, elementary row operation you want to be done on A, do it on identity first, you will get a matrix. So, store that matrix, once you have stored that matrix, multiply the matrix A on the left side by that matrix, the resulting matrix will be doing that operation on A. So, if you want to interchange two rows, take identity matrix, interchange its rows, you will get a matrix, pre-multiply A with it, the resulting matrix will be the one where rows of A are corresponding rows are interchanged. If you want to add, do the same thing for identity matrix, add the corresponding rows, identity matrix, you get a matrix, pre-multiply with A with this matrix, the corresponding rows will be added. And similarly, right, if you want to multiply and add or interchange, same thing you do here and apply it there. So, for all three elementary row operations, what are the three elementary row operations? One was interchange of rows, the other was multiplying a row by a scalar, and the third one was multiplying and adding. These three operations you can do on identity matrix and store them, and whenever you want to do this operation on A, pre-multiply A with that matrix. So, computer will store in the computer those things and do that multiplication on the computer to do those operations, right. So, these matrices are called elementary matrices. What are elementary matrices? These are the matrices obtained from the corresponding identity matrix by doing elementary row operations on them of three types, right. So, there are three types of elementary matrices which are used to do elementary row operations on any given matrix, right. So, we will continue study of these elementary matrices next time.